This lesson is over complex numbers. Recall, a square root of a positive number. Is that possible? Yes. Can we take the square root of 0? Yes, because 0 times 0 is 0. Can you take the square root of a negative number? No. So the square root of a negative number is not a real number, which leads us into the imaginary number, which we represent as the letter I. I really means the square root of -1, and we also use the fact that I squared equals -1. Example 1, express each number in terms of I. For A, we have the square root of -28. Well, since we have the negative attached to 28, I want to kind of move it away by rewriting it as the square root of -1 times 28. Since I've made it into two separate values, I now want to write it as two separate radicals. Square root -1 times square root 28. Now, -1 cannot factor, but 28 can factor, which would give us square root -1 times square root of 2 times 2 times 7. Now we want to simplify the problem. Square root -1 we just learned can be represented by what letter? I. Now we look at the radical and we want to see if we have any sets under the radical that can be pulled out. Notice we do have a pair of 2's, so that comes out of the radical, but notice the 7 does not have a set, so it will remain square root 7. Since I have I times 2 times square root 7, since they're doing the same operation, I can't reorder that, and I'd prefer to see it as 2 square root 7 I. We treat the I like a variable, and the variables are always on the back side. So this would be your answer. For B, I have negative square root -9. Again, our focus is the negative under the radical. So I rewrite that as negative square root -1 times 9. Now I want to take a moment. Because there's a negative on the outside and there's one on the inside, they cannot join. The negative on the outside must stay on the outside. If you felt the urge to multiply those two, make a note that you cannot do that. Alright, so since we've separated -1 and 9 under the radical, we're now going to separate it into two separate radicals. So we have negative square root -1 times square root 9. Since I have radicals, I want to, if possible, reduce them, but in order to do that, I need to see everything factored. We still have the negative on the outside. Square root -1 cannot be factored, but square root of 9, well, 9's really made up of 3 times 3. Now that everything's factored, we're ready to start simplifying, if at all possible. The negative on the outside is still there. The square root of -1 we now know can be represented by the letter I. And then under the square root we look for sets. Notice we do have a pair of 3's, so it comes out. And since there's nothing else left under the radical disappears. So we have a negative I times a positive 3, which together gives us -3I, and that would be your result. For C, we have the square root of -15. This is your try it problem. Hopefully you found it to result in the square root of 15I. Make sure your I is not under the radical. That would be incorrect. Alright, so we now know about this imaginary number that leads us into a complex number. A complex number is a number of the form a plus bi. Well, what does that mean? The a represents the real number, bi represents the imaginary number. Now the order is very important. The real always comes first, the imaginary always comes last. Now the good news is complex numbers obey the associative, the commutative, and distributive laws. Example 2 says to simplify. For a, we have negative 6 minus 5i minus the complex number 9 plus 2i. Well, how do you simplify this? Easy. We follow order of operations, or GEMS. Do we have grouping symbols? Yes. Can you do anything inside the grouping symbols? No. Do we have any exponents? No. How about multiplication division? Well, this is where it gets tricky. Since we have parentheses, we have to look immediately in front to see if anything needs to be distributed. In front of the first parenthesis set, notice there is no number in front of it, which means the parentheses are no longer necessary, so we can confidently write that as negative 6 minus 5i. The second parenthesis set has a minus sign in front of it, which can be interpreted as the opposite of. So the opposite of 9 and the opposite of 2i results in negative 9 minus 2i. So we did distribute. We've taken care of multiplication division, now we move to subtraction and addition. In other words, combine your like terms. Now, is the order important? Yes. Since we have real and imaginary, we need to pay close attention to how we gather them. We need to gather our real numbers first. Negative 6 minus 9 gives us negative 15. Now we gather our imaginary, and we have negative 5i minus 2i, which gives you negative 7i, and that would be your simplified answer. I clearly see the real number and the imaginary. For b, we have 3 plus the square root of negative 16 plus 2 plus square root of negative 25. Now this one looks slightly different, but notice we have radicals, and specifically, what do we have under the radicals? We have a negative. And we learned when you have a negative under a square root, what letter is introduced? Well, that would be the letter I. We have it in the first parenthesis set and the second parenthesis set. So we've now taken care of the negatives, but now we want to go back and, if possible, reduce the radicals. What's the square root of 16? 4. So we can now write that as 4i. The second radical was square root 25. Well, the square root of 25 is 5, but we can't leave behind the I. So we now have the complex number 3 plus 4i being added to the other complex number 2 plus 5i. From here, we again follow order of operations, or GEMS. Can we do anything inside the grouping symbol? No. Any exponents? No. Multiplication division? Not sure, but we need to look. Since we have the grouping symbols, we need to look directly in front of it. In front of the first parenthesis set, there is no value that needs to be distributed, so we can write that without the parentheses and leave it as 3 plus 4i. The second set, we look directly in front of it. Because it's a plus or a positive, that means there's no sign changes and there's nothing to distribute. So again, we can remove those parentheses and leave it as 2 plus 5i. We've checked multiplication division. We're now ready to check into subtraction and addition. So when we collect our like terms, remember we must collect the real values first. 3 plus 2 is 5. And then the imaginary 4i plus 5i is 9i. And that would be your simplified answer. Again, we clearly see the real and the imaginary. So we've talked about how to add and subtract complex numbers. Now let's talk about multiplication. When square root a and square root b are real numbers, then square root a times square root b can equal the square root of a times b. But when square root a and square root b are not real numbers, square root a times square root b does not equal the square root of ab. Now you may be thinking, what does all that mean? Let's look a little closely at it. Notice it says when square root a and square root b are real numbers. Real numbers means when you have positive numbers under the radical. So if you have positive numbers under the radical, they can be joined together under a single radical. Now the second statement says when square root a and square root b are not real numbers. Well, when do we encounter not real numbers? Well, that's when we have negative numbers under the radical. So if you have negative numbers under the radical, you cannot join those radicals together until you deal with the negatives. Let's look at an example. So let's look at the following. We have the square root of negative 2 times the square root of negative 5. Can I put those two radicals into a single radical? No, I cannot because I have negatives under the radical. So we have to address that first. Well, the first radical has a negative, which means what letter just got introduced? I. Now the second radical also has a negative under the radical. What letter just got introduced there? That too would be the letter I. So I can now rewrite this as I times the square root 2 times I times the square root 5. So I've taken care of the negatives under the radicals, and now I see clearly what I am dealing with. Now notice, all of those are multiplying. I mean, I times square root 2 times I times square root 5. Since it is the same operation, we can rearrange, we can shuffle them around like dominoes. And so what I want to do is I want to move my variables, I, to the back end and have my numbers towards the front. So I would rewrite it as square root 2 times square root 5 times I times I. Now that they're kind of categorized, now I want to simplify if at all possible. Notice square root 2 and square root 5. They're both positive values under the radical, and we just learned if it's positive under the radical, I can join them together under a single radical. Now looking at my i's, instead of I times I, what's another way to write that? Well, that would be I squared. So we've gathered our radical values and we've gathered our i's. Now let's see if we can simplify. Under the radical, I have a 2 and a 5. Can I pull out any sets to simplify? No. So we will leave it as 2 times 5, or square root 10. Now we're looking at the I squared. Now remember, earlier in your notes, we stated the imaginary number is I equals the square root of negative 1, and I squared has its own value. What is the value of I squared? Well, that is negative 1. And so I have square root of 10 times negative 1, which means your final simplified answer would either be negative square root 10 or you could write it as negative 1 square root 10. Example 3, the directions say to simply multiply. For A, we have the square root of negative 49 times the square root of negative 9. The first thing you may notice is we have a negative under the radical, which means what letter just got introduced? Well, that would be I. The second radical also has a negative under it, which means what letter just got introduced? Another I. So we want to simplify this. We've taken care of the first negative, which we know is represented as I. Do you know the square root of 49? Yes, it's 7. Now the second radical, we know the negative means we now have introduced I. But do we know the square root of 9? Yes, it's 3. And so since we've got all the terms before us, now we're going to simplify it. Looking at our numbers, we have a 7 times 3, which we know is 21. And I times I can be rewritten as I squared. Although it seems like we've simplified it, we have to remember I squared has its very own value, and that value is negative 1. And so we're left with 21 times negative 1, which gives us For B, we have the complex number 1 plus 3i times the complex number 1 minus 4i. Now, what does this look like? Well, it looks like a binomial times a binomial, which simply means we will distribute or FOIL. So we distribute the 1 as 1 times 1, then 1 times negative 4i, which gives us 1 minus 4i. Next, we distribute the 3i. 3i times 1, 3i times negative 4i, which gives us 3i minus 12i squared. From here, we want to see if we can combine any like terms or anything. And so first we have just a 1. But in the middle, notice we have negative 4i plus 3i. Those are like terms and combine to give us negative I. Now the negative 12i squared, remember, when you see I squared, what number takes its place? Well, that would be negative 1. So we can rewrite this as negative 12 times negative 1. Still following order of operations or gems, I need to take care of that multiplication. Negative 12 times negative 1 produces a positive 12. From here, I want to gather my like terms, but because I have real and imaginary, I have to pay attention to the order. We must gather our real number first, which in this case 1 plus 12 is 13. And then our only imaginary is minus I, and so that would be your simplified answer. For C, we have 7 minus the square root of negative 16 times the value 2 plus square root negative 9. All right, notice under the radical, what do you see? Well, we have a negative. And anytime you see a negative under a square root, what letter just got introduced? That would be I. And we have it happening in the first value and in the second value. So we want to take the time to rewrite this. We know that there is an I under the first parenthesis, but what is the square root of 16? Well, that's 4i. The second parenthesis said we've taken care of the negative, but what is square root 9? 3. So we can rewrite that as 3i. So we now have 7 minus 4i times 2 plus 3i. From here, since it is a binomial times a binomial, we will distribute. 7 times 2, 7 times 3i would give you 14 plus 21i. Next, we distribute the negative 4i. So negative 4i times 2, negative 4i times 3i would give you negative 8i minus 12i squared. From here we want to gather any like terms if possible. There's only one constant, which is 14, but in the middle we have like terms. 21i minus 8i gives you 3i. The last term, notice, you have an I squared, which has its own value of negative 1. So we rewrite that as negative 12 times negative 1. And so since multiplication comes before addition, we need to take care of that. Negative times a negative is a positive, so it will become 14 plus 3i plus positive 12. Now all we're left with is addition, so we gather our like terms, but remember, you have to gather your real numbers first. So 14 plus 12 is 26, and then our imaginary is plus 3i, and that is the result for C. For D, we have 2 minus 5i, quantity squared. Well, remember, an exponent means that value times itself that many times, which means we need to take the time to rewrite this. This really means 2 minus 5i times 2 minus 5i. Take a moment now to go ahead and multiply and finish this, and let's see what you find. Hopefully you found the result to be negative 21 minus 20i. For E, we have 6 minus 8i times 6 plus 8i. This is your try it problem. Let's see how you did. Hopefully you found the result to be 100. Now, notice there's something different about this result. This result was a real number. It wasn't complex, meaning it didn't have a real and an imaginary. This just had real. What do you think caused this to happen? Well, go back and look at the very beginning, the problem of E. On E, notice we had the same terms, but different signs. Both parentheses had a 6, both parentheses had an 8i, but they had different signs. One was a plus, one was a minus. Whenever you have that, that is known as complex conjugates. The good news is the product of complex conjugates is a real number. Remember, product simply means to multiply. So it means the multiplication of complex numbers will be a real number. And we just saw it happen on E. Why might this be useful? Well, the use of conjugates is helpful when radicals and imaginary numbers appear in the denominator. So let's look at an example. Example 4 says to divide. We have the complex number 5 minus 3i divided by 4 plus 3i. Well, notice we have an I in the denominator and we cannot keep it there. So we said the way to get rid of it is to multiply by its complex conjugates. So what does that look like? Well, it means we start with the original fraction. Our focus is on the denominator. In the denominator, I have 4 plus 3i. Well, its conjugate would mean I'm going to have the same terms, but the opposite sign. So instead of 4 plus 3i, I will multiply by 4 minus 3i. However, I have to maintain the value of this fraction. So what you do to the bottom, you must do to the top. And so what we currently have is a fraction times a fraction. How do you multiply two fractions? Well, top times top, bottom times bottom. So we are going to do some work on the side of our paper. For our numerators, we are being asked to multiply 5 minus 3i times 4 minus 3i. Take a moment now to multiply that and find the result. Hopefully you found the result to be 11 minus 27i. Now the denominator has 4 plus 3i times 4 minus 3i. So again, on the side of your paper, take a moment now to multiply. Hopefully you found the result to be 25. And so our fraction, our result, appears to be 11 minus 27i all over 25. Now it is a great answer, but it's not in the correct form. It has to be in the form of a plus bi. I have to be able to clearly see here's my real value, here's my imaginary. So we will need to separate this. The real, which was 11, is now over 25. The imaginary is the 27 over 25. And then we have the I, the variable, off to the side. So your final answer is 11 over 25 minus 27 over 25i. Now neither of these fractions can reduce, so that is your final answer. Now, let's go back and answer the equation that originally brought us to this topic. We were looking at 3x squared equals negative 12. Now in this equation, notice we only have x squared, so we need to isolate it. In order to get x squared by itself, we need to divide the left side and the right side by 3. When we do so, that gives us x squared equals negative 4. Now, although we've gotten x squared by itself, I want to get x by itself. So how do you undo squaring something? Well, you take the square root. As long as what you do to one side, you must do to the other. But don't forget about the plus or minus. Now the square root of x squared does give you x, but on the right side, we now know, since we have a negative under the radical, what letter is introduced? I. And so we have taken care of the negative. Now we're left with the square root of 4. What's the square root of 4? 2. So we're left with plus or minus 2i. And again, we do need to separate this into separate answers. So we would have the positive version, which would be x equals 2i, and the negative version, x equals negative 2i. And these would be your two solutions.